Last part of today would be our last part of the transport layer, and we'll be taking flow control protocols. I gave an introduction of what basically flow control is, in which the process controls the rate at which the data is transmitted. Okay, the process here controls the rate at which the data is exchanged between the two nodes. It also involves a feedback mechanism. I think I better put the video off, it might cause a lag. It involves a feedback mechanism. What is this feedback mechanism? It informs the source machine that destination's machine's ability, the ability of the destination machine to keep up with the current flow. Am I able to receive this flow or not? And in flow control, normally source node may not transmit frames until it receives a permission from the destination machine. Okay, please start sending. And we also discussed that we would require a balance between the two, between the sender and the receiver, which I mentioned as production and consumption rates. The faster the production, you can overwhelm the receiver. The slower it is, it will be less efficient. And what flow control deals with? The flow control has to deal with prevention of data items at the receiver end. Then we also discussed two things, that was pushing and pulling, in which pushing, whenever the sender sends the data without actually getting the permission. The second one was pulling, where the receiver requests the sender for the delivery of data items. Then we took the brief introduction about buffers. We would require buffers at both ends, the sending end as well as the receiving end. We saw that as well. Now, flow control protocols are divided between two. One is for noisy channels, another is for non. But before that, let me add just one more thing. We have two things here. One is the sequence number. Another is the acknowledgement number. I have sent the notes for flow control in the Google Classroom for your reference. Let's first take the sequence number. Both of these, sequence number as well as acknowledgement number, we discussed when we took the segment structure, when we took the structure of the TCP header. Okay. Now, what is sequence number here? For error control, we require that the sending transport layer knows which packet is to be resent, and the receiving transport layer knows which packet is duplicate or which packet has arrived out of order. How can we know if packets are out of order? How can we know packets are duplicate? How can we know packet is to be resent? This all can be solved if packets are numbered. you give the numbering to the packets, packet 1, packet 2, packet 3, and so on. So this is where we give a number to the packet. If we have, let's say, this as a bigger segment, you have divided it into a number of segments, then you say this has a sequence number as 1, this has a sequence number as 2, this has a sequence number as 3, and so on. So this is where actually sequence number helps. You are numbering the packets. Now, once we have a sequence number and you send the data across, the receiving transport layer can also detect if there are duplicate packets or not. How? If it receives the sequence number 3 twice, it obviously means it's a same sequence number, it's a duplicate packet. How would you reorganize the packets? If this is what the source has sent, you would separately get 1, separately get 2, separately get 3. In this case, you would have a numbering in the packet. That is the sequence number. And the receiver at the receiving end would obviously use this sequence number to compile back the message, putting on the first packet first, then the second one, then the third one, and so on. This is how sequence number helps, by changing out of order packets in order using the sequence number. And keep in mind, sequence number, packets are numbered sequentially. All right. Since we have to, they are numbered sequentially. Since we have to, let me just. Since we have to, include the sequence number of each packet in the header, so there has to be some limit. What is the limit? If the header of the packet allows m bits for sequence number, we can have a sequence range here. How much would be the range of sequence number? So if header allows, let's say, m bits, for example, I'm thinking for sequence number, then range of sequence numbers will be starting from 0 to 2 to the power of m minus 1. Just try to write m somewhere here. Oopsie. Where we go? Oops, this has gone. I was annotating. Anyhow, so in sequence number, I would have 2 to the power of m minus 0 to 2 to the power of m minus 1. That would be the range. The second part is acknowledgement number. Now, in acknowledgement number, what is this acknowledgement number? When the receiver receives a packet, it sends back a signal, a message to the source that yes, I have received this packet, this specific packet, right? Or a collection of packets. So receiver can send back an acknowledgement for each of a collection of packet that has been arrived safe and sound. What if a packet is discarded? What if a packet is corrupted? The receiver can simply discard it. Once the receiver discards the packet and does not acknowledge this packet, the source within that timeout, after the timeout, would get to know that, okay, destination has not received this packet. Let me resend it, and the source resends the packet. So receiver discards the corrupted packet. The sender can detect the lost packet if it uses a timer. What was the timer? When the packet is sent by the source, the sender starts a timer. If the acknowledgement does not arrive before the timer expires, then the sender would obviously resend the packet. Also, it's not only the corrupted packets that are discarded. I'll say here, corrupted packets are discarded. There is another thing, that is duplicate packets. Duplicate packets are also discarded. Keep that in mind by the receiver. And third thing is out of order packet. In this case, in out of order packets, there can be two conditions. One is if the receiver has a buffer, it stores until missing ones arrive. So if we know TCP uses inter packet delivery, so however, if because of IP, some packets arrive early, some packets arrive late. So just now we took an example of 1, 2, 3 packets. If one arrived first, then 3 arrived. If the destination uses a buffer, the receiver can receive 1, keep the packet 3 in the buffer until 2 arrives. Once 2 arrives, it puts them in order and the message is back. So it does not need to discard it. However, if it doesn't use that buffer, it can simply discard. So it can be stored or discarded depending upon the receiver. So this is where we use the acknowledgement number so that we acknowledge back the packet that has been received. Now, coming to flow control protocols. What are flow control protocols? We would require protocols to simply tell the source whether the speed at which you are sending is okay or not. The first one is known as simple protocol. Actually, it's not protocol itself. This is a connectionless protocol with neither flow or error control. Now, what does this simple protocol say? We can assume that the receiver can immediately handle any packet it receives. In other words, the receiver can never be overwhelmed with incoming packets. This is an assumption that we make in a simple protocol. So as such, it's not a flow control protocol either. Then we have stop and wait protocol, flow control protocol. So this is the first flow control protocol that we have, what we call as stop and wait. It's a simple protocol in the sense that firstly, it's connection oriented. It has both flow as well as error control. simple, connection oriented, flow and error control. It has both flow and error control. Now, what do we have here? It requires the sender to simply transmit one frame at a time. Let me draw a figure here to understand it. So this is our sender, this is our receiver. I don't know why this gets lost. Let me just we have a sender here and we have a receiver here. What does stop and wait say here? Okay. Now, both sender and receiver use a window. Okay. And what is this window? Window is of size 1. Remember this we took in the format when we saw TCP. There was, let me go back. There was a field. And the name of that field was, this is UDP, I think it will be after it. Okay. See here. Flow control, receive window, number of bytes receiver is willing to accept. So we have here a mention of the window size, how much it can actually accept. Okay, so where was I? Yeah, here. So this is where we use this window size. And in stop and wait flow control protocol, we have a window size of 1, which also means that sender sends one packet at a time and waits for the acknowledgement before it starts sending the next packet. When the packet, so if I send a packet here, Raman, can you confirm what you are watching this time? What you are seeing in the display? Okay. Why I got some delays here. Let me. Okay, can you see flow control protocols now? Okay, fine. So in this case here, I will send a packet first. So this is my first packet. This is sent to the destination. And the receiver receives this packet here. And it starts with the timer. What is the timer? Basically, it expects that during that time, it should get a receiver. It should get a reply. So let's say this is the timeout. This is the time. And when the receiver receives this, when the packet is received at the receiver side, it is checked. Obviously for errors and so on. It checks the checksum as well. If the checksum is incorrect, the packet is obviously corrupted. The packet is discarded. If the packet is discarded here, I will delete it. What would happen? Timeout would happen. And where is the timeout? Here you can see this is the timeout. Okay. And if this timeout has happened, what is the sender supposed to do? Sender is supposed to resend the packet. So we will have here the same packet resent in this case. This is the first condition. In second condition, if we normally receive the packet before in this, there was no error within the packet. Before the timer expires, we will get an acknowledgement. We will get an acknowledgement from the receiver. So we have, and I have this as, let's say, this one as acknowledgement. And the same acknowledgement is received by the sender. Now, once this acknowledgement has been received, the sender, after receiving it, would prepare the next packet and send the second packet. And this packet would be received by the destination, the second packet. And once this packet is received by the destination, it obviously sends the acknowledgement. This acknowledgement is again received by the sender, and the sender prepares the third packet, and third packet is sent across. And this is how this stop and wait protocol works. Why we call it as stop and wait? Because it requires the sender to transmit one frame and then wait for the receiver to acknowledge the receipt of that frame. What is an acknowledgement? It's a basic frame. Acknowledgement, the one which I have depicted here as a yellow colored packet, it's a basic frame without any user data. And what is the purpose of it? It would have the acknowledgement flag set on in the TCP header. And its purpose is to simply inform the sender that receiver is ready to accept another frame. I have received your previous one. Send me another one. I am ready to accept it. And sender will not send the next frame until it receives an acknowledgement of the previous frame. So to send the next frame, to send the next packet, it has to wait for the previous one. If the receiver does not acknowledgement, so obviously the sender would have to wait for the timeout, then only it would send the next packet. This also means two things. One, that the sender has to wait till acknowledgement is received, and also sender has to keep the copy of the packet that it has sent until it has received the acknowledgement. Why would sender need to keep a copy of the packet until acknowledgement arrives? Because it doesn't know whether it has been safely received or not. Once it receives the acknowledgement, then it can discard the packet because it knows now I have received it. Right? Also, the receiver has to ensure that it keeps the acknowledgement with it until it receives the next packet. Or the receiver can generate a duplicate packet, delete one and send acknowledgement once again. Once it knows that, okay, why it has sent another packet, maybe because the sender has not received its acknowledgement. So in all, we have only one packet and only one acknowledgement that can be in the channel at one time. Right? So bidirectional, but it uses actually, the channel is bidirectional, but it uses simplex transmission. Why is it simplex transmission here? Because data flows in one direction only. Send, wait for it, then you receive. Okay. So the problem is it's a simplex transmission, number one. And number two, it is ideal for transmitting large frames. Large frames are generally partitioned into smaller data units. Why? We have to accommodate the MTU and so on, and also we have to accommodate receivers limited buffer length, buffer size. Another reason for smaller packet size is it can help, it can facilitate in faster error detection. That's the help it is. And the third reason we have smaller packets rather than larger frame is that it can reduce the amount of data required for retransmission. So if a big packet is lost, the whole big packet is to be resent. But if this packet was sent as small chunks, only those small chunks are required to be resent. Keep these three things in mind. That problem with this flow control stop and wait, and it's ideal for transmitting large frames, large packets, large segments. But ideally, we do not transmit large frames. Why so? There are reasons for it. Let me just write them here. The first reason that we have, why don't we generally say, because we have to take care of receivers limited buffer size. That's why we break it. Small size means faster error detection, and also small size means reduce the amount of data required for the transmission. Fine. With respect to this control protocol stop and wait, to prevent the duplicate packets, obviously what do? We use sequence numbers and acknowledgement numbers. And how do we number this stop and wait flow control protocol? If our sequence number is X, we only use X plus 1 after that. There is no need for X plus 2, there is no need for X plus 3 and so on. How? Let's take an example. Let's say a sender has sent a sequence. Let's try to understand this. What I meant by, let me just add this here. For sequence number, we have either X and X plus 1. That means it goes as x plus 1, then comes back x plus 1, then so packet 0, packet 1, packet 0, packet 1, packet 0, packet 1. We do not need to have packet number 3, sorry, packet number 2, that's x plus 2, 0 and 1 on 0 and 1 on. Why? Let's understand this. Send a packet with a sequence number x. Fine. The packet has arrived safe and sound here. Well, let me just put it here. I think it's better. So I have here sequence as x. And the packet x has arrived at the receiver. Fine, is safe and sound. What does the receiver do? Receiver sends an acknowledgement number. So this is an acknowledgement number that we receive for this packet. I'll say ACKX. This is an acknowledgement for the packet X. This was received by the receiver. Okay. If it was not received, the sender would send this packet number X once again after the timeout. Again, in this case, once the receiver receives it, it would send the acknowledgement. Condition is acknowledgement is corrupted, then again the sender sends it after the timeout. That is kept by the sender until it is safely received by the receiver. X is kept as a duplicate, so duplicate packets are sent, right, because of the sequence number. And the receiver can recognize that it's a duplicate packet because it expects the next packet to be the next sequence number, that is x plus 1, but packet x was received again, so it's a duplicate one. Thus, you would either require x or you would require x plus 1, because the receiver can have either safe delivery of packet and safe delivery of acknowledgement, or it has corrupted delivery of packet, no acknowledgement is sent, and the third condition is safe delivery of packet but corrupted acknowledgement or lost acknowledgement. Now there is a need for sequence number x and x plus 1 because receiver has to distinguish between number 1, that is either it has been received safely, or number 3 in which acknowledgement is corrupt. There is no need for a packet to be numbered x plus 2 here. In the first case, the packet can be numbered x again because packet x and x plus 1 are acknowledged. There is no confusion here. X is received, acknowledgement of x is done. X plus 1 is sent, acknowledgement of x plus 1 is sent. Because it's stop and wait, right? Until x plus 1's acknowledgement is received, it will not move to the next packet. Once x plus 1's acknowledgement is received, then only it will move to x once again. In this case, what is this third step? X plus 1 and then x. X is packet number 3. Is this clear? This also means that sequence is 0, 1, 0, 1, 0, 1 and so on. So if x is 0, x plus 1 is obviously 1. What would be our sequence number range from? It would range from 0 and 1, 0 and 1 and 0 and 1. This is known as modulo 2 arithmetic. So 0, 1 and so on. This would be how it would range. And this is what we have as modulo to arithmetic. Modulo to arithmetic. Do you have any questions for this? Any questions? Fine. Another thing, okay, I have a question here. Is it simplex or half duplex? Marine asks it. Okay. For the answer for this question, it uses simplex transmission. Even though the channel can be bidirectional here, but it uses simplex transmission. Why? Data flows in one direction only at a time. You sent it, then you then you wait for reception of the acknowledgement. So it is a simplex data transmission for stop and wait. All right. So another thing here, X plus 1 we did for the sequence number. How about the acknowledgement number? Acknowledgement number for stop and wait always announces the sequence number of the next packet expected to be received. What does this mean? This means packet 0 is, let me go back here, right. Let's have a look here. If packet X, which is supposed to be, let's say, packet 0, if packet X was the sequence number of it, if it was the packet 0, this packet 0 is received here by the receiver. It arrived safe and sound, error free. Then the receiver sends an acknowledgement number which is X plus 1. So X acknowledgement here is X plus 1. What does that mean? Packet number is 0. Acknowledgement number is equal to 0 plus 1. That is 1. So acknowledgement here is received as X plus 1, which is 1. What does it mean here? It means that the receiver sends an acknowledgement saying that I expect packet number 1 to be sent next. Do you get it? If packet 0 is sent, it doesn't say, in simple English, it doesn't say I have received packet number 0, even though it means to say that I have received packet number 0. It says I am now expecting packet number 1. So acknowledgement number is sequence number plus 1. Keep that in mind. It's an important thing that you have to remember here. And what is the acknowledgement for packet 1? Now in this case, if this is packet 1, so this is, let's say, packet number 1 now sent. And what is the value of the sequence number? Obviously X plus 1, because it ranges between X and X plus 1 only. So I have here X plus 1. That is supposed to be packet number 1. Now in this case, if this X plus 1 is arrived safe and sound, that is here, what do we expect the acknowledgement to be now? Anybody? Yes, we would expect an acknowledgement here for packet number 1 to be X, or simply what? I have received packet number X plus 1 and I am expecting packet number X to be sent because it ranges between 0 and 1 and 0 and 1. 0 received, send me 1. 1 received, send me packet number 0 now. So we have a task here which has begun before the previous task has ended, because you are saying that send me the next packet. This is a task which is begun before the previous task and ending. This we call as pipelining. I mentioned here pipelining. We have pipelining here. And what is pipelining here? You start a next process before it's done. But in the case of stop and wait protocol, there is no pipelining as of now. So I will say here, no pipelining. A task often begun before the previous task is ending. And in stop and wait protocol, there is no pipelining because sender must wait for a packet to reach the destination. Be acknowledged, then only the next packet is sent. So we do not see pipelining happening in stop and wait protocol. Is this clear? Do we have any questions? Any questions? No, then we move to the next protocol, which we call as go back and protocol. This is the picture which shows the stop and wait protocol. Actually, we just made the figure of the same. You see here RTT. RTT is basically based on the timeout that we have. Here it shows the utilization as well. So I might give you a question, a task, an assignment in which if we have a stop and wait system, I'll give you the bandwidth, I'll give you the round trip time also. You can find the bandwidth delay product, that would be simple. Then I can give you the length of the packet as well. You can give me the utilization of the link. So we saw that certain disadvantages like simplex transmission, it's only ideal for transmitting large frames, but we don't actually transmit large frames there. And there is no pipelining in the go back and end protocol. In pipelining, we could send many packets and then we wait for the acknowledgement of packets one by one. So we could have sent range of sequence numbers, and then based on the buffers that we have at the sender and receiver, we could have managed, receiving acknowledgements of 5 packets, 10 packets at one time. But this pipelining is not available in stop and wait. So to improve this, to improve the utilization of the link, to improve the performance of the flow control protocol, we use pipelining. What is this pipelining here? You send a certain number of packets, like here we have shown you three lines, three color, this in yellow, in blue color. Okay. And after sending these 3, we expect acknowledgement of each. So they can be acknowledgement given one by one. There can be a cumulative acknowledgement. Thus, it would improve the performance by a factor that is given here. Let us understand how this is done. For this, we take an example of back N protocol. This is also known as GBN. So first thing is we want to improve the efficiency of transmission. How do we improve the efficiency of transmission? Obviously, this is basically what we use as pipeline. You fill the pipe. How do you fill the pipe? You push in the multiple packets in the transition, and then the sender would wait for the acknowledgements of these. Rather than giving one file to say Ramanand, I'll give 5 files and I'll expect him to, give acknowledgement of each file separately or cumulatively. Now let's see how this GBN would work. So we do pipelining here, we fill the pipe. Multiple packets are sent in transmission, and what is the sender doing now? It's waiting for its acknowledgement. So it's an enhancement of stop and wait protocol by improving the data flow. How? The receiver informs the sender that I have this much of buffer space available. This enables the sender to transmit that many packets continuously. So if it says that, okay, my buffer capacity is 10 packets, I can have 10 packets at a time. So you can inform the sender that send me 10 packets. So sender transmits these 10 frames continuously without having to wait for the acknowledgement of each one by one. As long as the buffer is not overflowed at the destination, this protocol is fine, because you have already mentioned the 10 packets. So you send these 10 packets, you are not overwhelming the receiver. Also, sender sends sequentially. It has a sequence number for each data packet. Sender and receiver, they both maintain information about how many packets have been sent and how many have been received, because both of them have sender buffer, both of them have a receiver buffer. So why do we call it as go back N? Go back N protocol, because sender is allowed to transmit multiple packets when available without waiting for acknowledgement. It is constrained to have no more than a maximum number of unacknowledged packets in the pipeline, which is given by here N, given in the window size. So some maximum allowable number N is there. That's why we call it as go back N. The sender's window of up to N consecutive transmitted but unacknowledged packets. Let's understand it with an example. Here. Or before this, let's understand the sequence number. Let's understand the acknowledgement number that we did previously as well. The sequence number is again the modulo 2 arithmetic, 2 to the power of m, where m is the size of sequence number field in bits. This was similar to the previous protocol. Now acknowledgement number here, keep this in mind. The acknowledgement number here in this protocol is cumulative. I would write here. That's given here. Cumulative acknowledgement we have here. I'll come to this. As of now, remember, acknowledgement number in go back and protocol is cumulative and it defines the sequence number of the next packet expected. For example, if the acknowledgement number is 7, what does it mean? It means two things. First one is cumulative. What is cumulative? It means that all the packets with sequence number up to 6 have arrived. They have arrived safe and sound. And number 2 is that the receiver is expecting the packet with sequence number as 7. Is this clear? Right here, for example, acknowledgement number 7. So sequence number, we had numbers up to 2m minus 1, 0 to 2m minus 1. That is simple to understand. Start 1, 2, 3, 4, 5, 6, 7 and go up to 2m plus 2m minus 1. What is the m? M is the size of the sequence number field in bits, which we saw in TCP header segment field. That was field in the TCP segment structure. Now, once you have sent some packets here, obviously it's a pipeline. You send that many number of packets that the receiver can receive. Let's say you send 10, because 10 is the capacity of the receiver. Now, this thing is important here. What is acknowledgement here? We have a cumulative acknowledgement number. And what is this 7? If the receiver sends 7 back to the sender, this means two things. One, that all the packets up to sequence number 6 have been received, they have been error checked, they have been received safe and sound. And now I am expecting the sender to send the packet with sequence number 7. I'm expecting the sender to send the packet with sequence number 7. This is what we have, cumulative acknowledgement within go back and send. Is this clear? Is this clear? And this is referred to as sliding window flow protocol. Sliding window. Why do we have the sliding window here? What is this sliding window here? That's the next thing I'll be explaining to you. We have a window here which we call as a send window. Okay. You see, this is the picture that we have. So this go back and N is a sliding window protocol. And why do we call it as sliding window? Understand this as a send window. What is send window? It's a sender's window. And what exactly it is? It's an imaginary box covering the sequence numbers of the data packet that can be in transit or that can be sent. So consider this as an imaginary box. So there are different positions within this window. In each window position, some of these sequence numbers define the packets that have been sent. Let me annotate it. Okay. So let's start from here. This is the start of it. These have been already sent and already acknowledged. The green one means this much of transmission has already been done. Okay, so forget about this green part, already covered. Now we have the imaginary window, that is this. The size of this window is n. Those who have been sent an acknowledgement are out of it, which is this part. This is already taken care. Now, since window size is this much, we have some part which cannot be as of now used, all right, not usable. That is this part here which are shown. Forget about this as well. So this is where our window moves as of now. It has moved towards right because the left ones have already been acknowledged. It has been acknowledged. This has been taken care of. Now, within this window, we have certain slots which are given here. Right? They have been sent, but they have not been acknowledged yet. The yellow ones are sent, but have not been acknowledged yet. And also we have certain ones here which are not sent yet. Now what would happen here? Each window position here has a sequence number defined within it. Some are sent, already done, already acknowledged, taken out. But those who are sent or cannot be sent, whose acknowledge is not received, are kept within this window, and the size of the window here is given n. And what is the maximum size of the window here? Again, it's 2 to the power of m minus 1. Why? Because this is the maximum size that we have of the sequence number. This is the modulo 2 arithmetic. M is the size of the sequence number field in bits. Okay. We can have a fixed size of window like n here. It can be set to a maximum value, that is the maximum size we can have of the window. It can be that way as well. Some protocols may have a variable window size as well. We'll come to that as well. So let's say a window m equal to 3, we'll have a window size of 7. Okay. Now what do we expect within that 7? We'll have 7 different, let me just try to make it here. Let's try to understand this. Okay, so let's keep it from here. I have 0. Okay, now in this case, let's try to understand the go back and flow protocol. I have the send window send window is from here to here. This is my send window. This is the size of the send window that I have. Let's say window size is of 7 when I took m equal to 3. What are the packets that have been sent till now here, denoted by the green ones? These packets have been sent, these have been acknowledged, and these we are not concerned. Sent and acknowledged. This is fine. Now we are concerned with this send window. What are these on the right? Take these on the right. These cannot be accepted from the process. As of now, we cannot take them. So our main concern is the send window here. Let's say out of these, we have say the one we know from 0, 1, 2, and 3, these ones. Okay, these 0, 1, 2, and 3. These ones I would name as they are sent but not acknowledged. Fine. And then I would have some more here. Let me just change the color here. This is given by 4, 5, 6. These can be sent when accepted from the process, or these are the next to be sent. So this is what we have here. Go back and or sliding window. We have a window which moves on next to the right, and to the right, accepting the new packets. There are different regions within it. The first region that we see is the left of the window. It finds those sequence numbers that is given here 6, 7 belong to the packets that have been sent, that have been already acknowledged. The sender now does not worry about these packets. It does not keep copies of them because they have been already acknowledged. Fine. There is a second region, okay, which is here in orange color. This is given by 0, 1, 2, 3. Now this defines that range of sequence numbers which belongs to the packets that have been sent, but their status is not known yet. So their status is kept unknown. Why? The sender is waiting for their acknowledgement. The sender does not know whether they have been received or they were lost. So this sent but not acknowledgement and not acknowledged, we'll call them as outstanding packets. Then we have the third range. And what is the third range? We have a light blue color. That is for sequence number 4, 5, 6. And what does it define? It defines the range of sequence numbers for packet that can be sent. Okay, but the corresponding data, the data within these packets has not been received from the application layer as yet. So once the application layer sends this data, what would happen? Let's say it sends some more data. In this case, we will change 4 and 5. 4 and 5 would become like this, orange. Sorry. So in this case, if the application layer sends more data, it can be sent because there is certain space in the send window which has not been utilized yet. So this would happen. 4 and 5 would also be gone. And the acknowledgement of 0 and 1 is received, the 0 and 1 would change back to blue. What would happen to send window here? The send window in this case would move like this. See this? All right. We would have this green block also moved. So these many are sent and acknowledged. Send window moved towards the right. This also means that there are some more spaces here which can be accepted. So I would move this red also towards right, the one which cannot be accepted. We have some more space here. This is what we mean by a sliding window. The window would keep on moving or sliding once we get acknowledgements, right? Once we get more data, it will fill it, okay? But if 6, 7 and this 0 is also given, the data of these 3 is given already, then what would happen in this case? It will not move the window until and unless you get the reply from the previous ones. So if this is the situation, means window is full, it is sent but not acknowledged, the window cannot move. It cannot accept more data from the process that is towards the right. It will only move if 2, 3, 4 and so on gets acknowledged and so on. Is this clear? Any question till now? Any question about go back and receive? Now in this case we have to discuss the receive window as well. So what about receive window? This is sender window, the one which I showed you, send window. We would have a receive window also, and the receive window makes sure that correct data packets are received and the correct acknowledgement are sent. And the receive window would take 2, send back the acknowledgement of 2. It would take 3, send back the acknowledgement of 3. Or it would have a certain number of these and send the acknowledgement of these. The receive window is always size 1. Why? This would mean, for example, the previous one. I am sending back acknowledgement 7. All the packets till 6 have been received. Now we are expecting packet number 7. So the receiver is always looking for the arrival of specific packet once it sends back the acknowledgement. Let us clear this part. And we see one of the figures that shows this in action. This is the receiver, which it says the receiver is single window. It moves on. So if as of now it was here, it sent the acknowledgement of whatever was received till here, and it's presently moved to this one. So the receiver window would only be of size 1 in sliding window protocol or in go back N flow control protocol. Is this clear? So how this go back N works. The sender window has the window size of N. We are taking an example here in which packets 0, 1, 2 and 3 have been sent. Okay, this is how packet is sent. First 0, receive packet 0, send acknowledgement 0, send packet 1, receive packet 1, send acknowledgement 1. But the difference between the previous one wait protocol that we previously took, the stop and wait, is that we did not wait send 0 and waited for the acknowledgement of 0. Instead, we sent 0, 1, 2, 3 without waiting for the acknowledgement of 0, first, second, first and two. But after packet 0, 1, 2, 3, we did not go beyond because our sender window size is N. We'll only move beyond 3 once we get the acknowledgement of previous ones. In this case, we received 0, send 0, received 1, send acknowledgement 1, but 2 was lost. So this is what happens. Now, since packet 0 is received back here, acknowledgement of 0 is received here, this means our window N has some space here, one empty slot here, which is created because we received acknowledgement of 0. In this case, it sends the next packet because we have received one. It sees packet number 4 that is sent here. So receive packet 4, but it discards. Receive packet here 3, discard. Why? Because there was one of the packet that was missing here. It did not receive that in sequence. Then what does it do? It keeps on discarding until it ensures that the packet that was missing was resent. When is that packet resent? After the timeout of 2 happens. After the timeout of 2 happened, this packet was resent. Resent 3, 4, 5 once again. This is how the go back and works. The next protocol that we have is selective repeat. I think we would take that in our next class. Do we have any questions till now? Yes, Raman. No questions? Then we are left with selective repeat only. SR, we'll do it in the next class and we'll be done with flow control. No questions? Then I'll be ending the class. All right, I'll see you in the next class. Goodbye, everybody.